Hello, I'm 719 Lee, and Dr. His PhD student. This work is a collaboration with Linde. My research is related to development of fault detection method. So my presentation title is a statistic pattern analysis based k-nearest neighbor fault detection for pressure swing absorption process. First, I will give you a brief introduction on pressure swing absorption process and the challenges of monitoring periodic processes. Then I will talk about the motivation of this work. There are many process monitoring methods published. Why we need to propose a new one? This is because existing methods have limitations, and the proposed approach is intended to address them. I will talk about the new method in detail and compare it to existing method. Finally, I will draw the conclusion based on our findings. Pressure swing absorption is a well-known process to separate the product from impurity. PSA consists of two basic steps, absorption and desorption, and repeat these two steps. During the absorption step, the impurities are absorbed by adsorbent, producing the high purity product, while during the desorption step, the impurities are cleansed from the adsorbent, allowing the cycle to be repeated. This process has been used in a variety of different fields because it can produce high-quality product with a low energy and low capital cost. Although PSA process has been widely used in many industries, the process monitoring has received little attention. This is because there are many challenges of periodic processes. First, the cycle have a different trajectory. They do not exactly overlap each other. Also, process is highly nonlinear. The cycle duration changes from cycle to cycle, which result in multimodal process operation. These characteristics pose challenges to conventional multivariate statistical process monitoring methods. Several methods have been proposed to monitor the periodic processes. Although they improve the monitoring performance, there are some limitations to apply those methods to industrial PSA process. Since they require pre-processing steps such as trajectory alignment, they may be less efficient monitoring for dynamic change of process operation. Also, they have difficulty in dealing with high-dimensional data and nonlinearity. Therefore, we propose a novel method that aims to address these limitations. To address the previously mentioned limitation, we propose a new process monitoring method, namely SPA-KNN. The KNN method can be used for fault detection by using attribute. The distance between fault data and each neighbor is much larger than that between normal data and each neighbor. We hypothesized a periodic cycle behavior can be better characterized by the cycle feature than by the cycle process variable. Therefore, SPA-KNN can distinguish fault better by making a larger distance between the fault and its neighbors than that by KNN. The proposed method aims to capture the characteristics of pressure behavior in each step of a cycle through extracting statistic and shape features. This is a flow diagram of SPA-KNN method. The first step is a feature generation, where various statistical and morphological features are generated from each step of a cycle based on the log process data. As shown in the right figure, one cycle consists of several steps. Features are extracted from each step. Therefore, we can obtain the greater number of features than the number of process variables. These features are stacked row-wise to form a feature vector for each cycle, and multiple cycle features are stacked column-wise to form a feature matrix. The second step is to perform fault detection based on the feature matrix, where a KNN fault detection method is applied. Since features of a cycle consist of various statistical and morphological features calculated based on the log process variable, SPA-KNN can quantify process dynamics and nonlinearity. In addition, SPA-KNN naturally handles unequal step duration and asynchronous cycle trajectories through feature extraction. Lastly, the proposed method can address the challenge from the multimode process operation. Therefore, SPA-KNN is well suited for monitoring of PSA process. The table shows the statistical feature we have studied. Each feature can describe the different aspect of a characteristic of a PSA process. In this study, we utilized mean standard deviation, skewness, and mean absolute error. Mean and standard deviation are used to capture the overall change in each step because mean and standard deviation are measured of central tendency and variability, respectively. Skewness and mean absolute error are used to explain the shape of each step, since skewness explains the distribution shape of each step and mean absolute error measure the difference from the specific trend. One noticeable point is SPA-KNN is very flexible to include more features or eliminate the features based on the process characteristics. We used the industrial PSA case study to demonstrate the performance of SPA-KNN method. Among 5 fault scenarios, the first 4 are simulated fault, while last one is an actual fault from industrial data. The simulated faults are generated based on fault observed in actual operation. Due to time limitation, I will introduce third and fifth fault scenario. Third fault scenario is unexpected hold and sudden pressure drop. At the equalization step, pressure keeps decreasing, but when operation is out of control, we can observe the unexpected hold and then pressure sharply drop. Fifth scenario is a pressure mismatch in repressurization step. During repressurization step, the pressure of 40 cycle do not follow the normal cycle trajectory. In this study, we compare the proposed method to the 3 different fault detection methods: multi-wave PCA, KNN and standardized KNN. Before performing the fault detection for these three methods, we employ the dynamic time warping for each step to have the same duration. All the parameters are determined by cross-validation, and 99% confidence level is used for threshold. SPA-KNN has 69 input features, while other methods have 619 input variables. The input dimension of SPA-KNN is much smaller than other methods. This is because SPA-KNN can significantly reduce the dimension of input space through feature extraction. This is the result of fault detection and false alarm rate for all the scenarios. As shown in the table, SPA-KNN method can detect all fault scenarios and identify the root cause of fault correctly. Except for SPA-KNN, all the methods fail to capture some fault and misidentify the root cause of fault. SPA-KNN has a lower false alarm rate in training set compared to other fault detection methods. This is the result of scenario 3. According to the fault detection plot, all the fault detection methods can successfully capture the fault cycle without false alarm. However, only SPA-KNN correctly identified the fault step is EQ4, while other methods misidentify the root cause of fault. This is the result of scenario 5. All the fault detection methods except for SPA-KNN fail to capture the fault cycle. Again, only SPA-KNN successfully detects the all fault cycle and correctly identifies the fault step is repressurization. Further investigation is conducted to understand the reason for failure of fault detection method with dynamic time warping in detecting fault cycle under scenario 5. We suspect the failure is related to data preprocessing by the dynamic time warping. Therefore, we plot the original pressure profile of the test cycle. After dynamic time warping, as shown in the figure, the irregular discrepancy of the fault cycle diminishes. This is because the fault cycle is synchronized to minimize the distance between fault cycle and reference cycle. Dynamic time warping needs to be used with caution, as it can distort process trajectory and introduce bias, leading to missed detection of true fault. In conclusion, I would like to summarize the advantage of SPA-KNN method. First one is a better identification of process behavior. The feature can capture various process characteristics such as dynamic nonlinearity better than the raw process variable themselves. Therefore, we don't need to use a complicated model to explain the nonlinear process. Second, the model can be simple. SPA-KNN can significantly reduce the dimension of input space through feature extraction and does not require complex algorithm for multimode process. Lastly, it is easy to implement SPA-KNN method because it does not require unfolding and complex cycle alignment and synchronization. We appreciate NSF financial support. Thank you for your attention.